Alright guys, today's video is about topic 8.4 of the IB curriculum, strong and weak acids and bases. I'm just mixing it up slightly today. I'm going to fill in this worksheet rather than click through and narrate over a PowerPoint. If you would like to follow along and take notes, I've also provided a blank worksheet so you can print it off if you're one of those rare families that has a printer these days. Otherwise, just sit back, take it in, or maybe take some notes on a blank piece of paper to help yourself stay engaged. But we'll jump right in. So the essential idea for today, the pH depends on the concentration of the solution. The strength of acids and or bases depends on the extent to which they dissociate in aqueous solution. So we're going to really focus on this idea of dissociation or ionization today. Those two words can be used interchangeably. And then here's the understandings. You can read these yourself. They're in your textbook, they're in the Chem guide, whatever, but we are going to cover most of this today, and I'm also going to touch a little bit on some of the higher level content. The idea of Ka and Kb is going to come up as well. Okay, so the first idea here, the strength of an acid or base, it depends on the degree of ionization. Okay, so to start here, we're gonna look at acids first, and we're gonna look at this idea of a general reaction for the dissociation of an acid in water. So we can say that an acid is just some species that contains a hydrogen that can dissociate. Okay, so I'm gonna represent my acid as HA. Okay, A representing the the conjugate base of the acid, and H being a hydrogen that can dissociate. And we know that acids interact with water to make their conjugate base. So notice this right here would be the conjugate base of acid HA because I've removed the hydrogen ion, so now it's A-. And then I've also got the hydronium ion being formed here. Right there. Okay, so this is a general representation of the ionization of an acid. Okay, so this is the general formula for an acid. We're going to look at two specific cases here. So one acid we could talk about is nitric acid, which is a strong acid. And then we can also talk about weak acids. An example that I'm going to use of a weak acid today is the hydrogen sulfate ion. Okay, so I'm going to look at what the ionization reactions look like for these two acids. We're going to compare them a little bit. So nitric acid is HNO3. It's aqueous. It's going to interact with water, which is a liquid. And it's going to make the nitrate ion and the hydronium ion. Okay, now because nitric acid is a strong acid, this reaction actually proceeds 100% in the forwards direction, no backwards reaction. So I'm going to use this type of arrow rather than an equilibrium style arrow in that reaction. Okay, and you can see that's a little bit different than a weak acid like the hydrogen sulfate ion. I'm going to have to write this one a little bit small because I didn't leave myself enough space. So we've got HSO4-. It's going to react with water. And I'm going to just write the products below because I'm out of space. So this is acting as an acid, meaning it's going to donate a proton. So I'm going to end up with the sulfate ion and hydronium as my products. Okay, and note here, because this is a weak acid, I do want to make use of my equilibrium arrow because this reaction goes in both directions, okay? The forwards reaction, where we have our acid donating a proton, proceeds, but at the same time, we have our reverse reaction happening where the sulfate ion acts as a base, takes protons back from hydronium. Okay, and that's sort of the major way we can distinguish between a strong acid and a weak acid. A strong acid goes 100% to the ionized versions, whereas a weak acid, there's an equilibrium between the acid and its conjugate base. Okay, we can actually talk about strong and weak acids in terms of the strength of their conjugate base. So for example, if I am thinking of the nitric acid, the strong acid example right here, the conjugate base of nitric acid is the nitrate ion. Okay, and I already described nitric acid as a strong acid. I could also say that its conjugate base, which is the nitrate ion, is extremely weak, meaning that there's pretty much no measurable rate of the reverse reaction here, which is why I used only the forwards direction arrow. Okay, so in a strong acid, the conjugate base is extremely weak. Okay, it doesn't really perform the reverse reaction at all. Whereas when I have a weak acid right here, the conjugate base, so in the case of this reaction, my conjugate base is sulfate. And the conjugate base is stronger. There is a measurable rate of the reverse reaction as well as the forwards reaction. Okay, so there's an equilibrium happening here. Now, one way that we describe the strength of an acid, especially when we're talking about weak acids and ranking their relative strength, is to use the equilibrium constant for the ionization or the dissociation reaction. Okay, so in general, if I look back to my general reaction here, the equilibrium constant for this is going to be concentration of the products divided by concentrations of the reactants, okay? Remembering that water here is a liquid, a pure liquid, so I'm going to leave that out of my Ka expression. So the equilibrium constant would be concentration of A minus times the concentration of hydronium. I could also put H plus right there instead of hydronium, but you'll often see it written like that, remembering that those two things are interchangeable. Then original concentration of the acid on the bottom here. Okay, so that's the equilibrium constant for that general dissociation reaction. And because we're talking about an acid here, we call it the acid ionization constant, Ka. Okay, so we have this little A here. Okay, now just to give you an idea of what this might look like in the case of a specific acid, something like the weak acid example we looked at right here, the Ka expression would be concentration of sulfate, so the conjugate base, times concentration of, I'm going to just use H plus here rather than the whole hydronium formula. Totally allowed to write it like that, over concentration of my original acid, hydrogen sulfate. Not a 2 there, just a minus. Okay. Now, these equilibrium constants for different acids, we can actually usually look them up. Okay, there are quantities that are sort of constants that we're able to find. So here's an example of a Ka table, so an acid ionization constant table. And we can see actually the acids we talked about today are on this table. So nitric acid is considered a strong acid, and its Ka is high, about 20. Okay, it's not quite as strong of an acid as hydrochloric acid, but it's very, very strong, which tells you if you're looking at the expression for Ka, that just means that the concentration of the ionized parts is going to be higher than the concentration of the original acid that remains intact in solution. Okay? Now, if I go a little bit lower on my list, I get the hydrogen sulfate ion right here, and its Ka is 1.2 times 10 to the negative 2. Okay, so looking at that, it tells me that I have quite small concentrations of these ions relative to the concentration of the unionized, undissociated acid. Okay, so we can use Ka as a way of ranking the relative strength of acids. All right, let's talk a little bit about bases before we move on. So, just like I can write a general reaction for the dissociation of an acid, I can write a general reaction for the dissociation of a base. In the case of a base, I'm going to call it B. And it's going to interact with water. And it's going to be in equilibrium. So bases, when they're Bronsted-Lowry bases, they act as proton acceptors. So I'm going to end up making Hb plus as my conjugate acid of that base, and then hydroxide. Okay, so that's the general dissociation reaction for a base. The base ionization constant in general could be written from this. So that would be something like concentration of products, Hb plus, times OH minus, over original concentration of base. Remembering that I leave the water out of the equilibrium expression because it's a pure liquid. Okay, and then because I'm dealing with a base here, this is called Kb. A specific example of that, if I want to think of a weak base, our kind of classic go-to example of a weak base is ammonia, NH3. So a specific dissociation reaction would look like this. Na plus H2O reacts to produce ammonium. So it's accepted a proton, and hydroxide. Okay, and then the Kb expression for that specific base would be concentration of ammonium. I'm going to leave the state symbols out because I've gotten a bit lazy. Times concentration of hydroxide, all divided by the concentration of the original base, which was ammonia in this specific example. Okay, and just like the strength of an acid can be measured by the Ka, the strength of a base can be measured by its Kb, and we can look those up in a table. So here's an example of a Kb table. This one's nice because it shows you the proton transfer reaction, which is helpful. We can see ammonia, the base we just looked at, is right on there, and it has a Kb of 1.8 times 10 to the negative 5. Okay, so compared to some of the other bases on here, it's quite a weak base, but not as weak as something like aniline or hydrazine. Okay, so that's a ranking of the strength of bases based on their Kb, their dissociation constants. The last thing I want to point out, you will sometimes see strong acids listed on Ka tables, but you won't usually see strong bases listed on Kb tables. And that's because when we're dealing with a strong base, like something where you've got a group 1 metal and a hydroxide, you're not going to see an equilibrium. You're also not going to see the role of the solvent. So sodium hydroxide just dissociates to make hydroxide ions in the solution. And we don't talk about the role of water at all. Okay, so you won't usually see this listed on a Kb table. Okay, and this is another example because this is a strong base, we use just the forwards direction arrow, not the equilibrium arrow to show the reverse reaction. Okay, I am going to go on. I'm going to make a second video here, but I'm going to pause it there. So that was the first part.